Hi folks, in this next section, we're going to learn how to solve equations with variables on both sides of the equation. Up to this point, if we've had a variable like a, you've only seen it on one side of the equation, but this time you can see that a exists on both sides of the equal sign. Really, our strategy is going to be the same that we saw back in section 1.2. We want to simplify each side of the equation. The additional step is that then after simplifying, we want to try to collect all of the terms that contain the variable on one side of the equation. And then we'll just proceed in reverse PEMDAS order from there. So looking here, I have negative 4a, 10 minus 4a on the left side of the equation and negative 9a on the right side. And I can't do anything to simplify the left or the right side of the equation. And so the next job is to collect all the terms that contain a on the same side of the equation. Now, it doesn't actually matter whether I collect them on the left or the right side, but usually one method is faster than the other. In this case, because there's a 10 on the left side, as well as the minus 4a, I'd rather collect my a's on the right side of the equation so that the 10 is not on the same side as the a's, just to save myself an extra step later on. It's not wrong to collect the a's on the left side. You'll just, in this example, you would end up with another step to do afterwards. So I'm going to add 4a to both sides of the equation. Remember, the equal sign is like the dividing line for the equation. So I need to do the same thing on both sides of the equal sign. And I'm adding 4a because 4a is being subtracted from the 10. So adding 4a is the opposite of subtraction. Therefore, after adding 4a to both sides, I'm left with 10 equals negative 5a. Now, this looks more like the types of problems that we saw in sections 1.1 or 1.2. My goal is to get a all by itself now that a is in one place. To get a all by itself, I'm going to divide by negative 5, divide by negative 5, and I get that a equals negative 2. Now, it is important to check your answers. So I'm going to plug negative 2 in to the original equation. 10 minus 4 times negative 2 equals negative 9 times negative 2. And I get, let's see, 10, negative 4 times negative 2 is positive 8. So that's going to be like 10 plus 8. And negative 9 times negative 2, negative times a negative is a positive. So that's going to be positive 18. So this does check out. 18 equals 18. Let's look at another example. In this example, we do have some simplifying that needs to be done because I've got a number multiplied by an expression and a subtraction problem in parentheses. So I'm going to go ahead and do the distributive property. 3 times 3b is 9b. 3 times negative 4 is negative 12. So I've now simplified the left side of the equation. The right side of the equation, 1/4 times 32b is 8b, and 1/4 times 24 is 6. So I've now simplified the right side of the equation. Now I'm going to collect all the variable terms on one side of the equation. Here, there's a negative 12 on the left, a positive 6 on the right. So it doesn't really matter whether it's the left side or the right side where I'm collecting numbers. I, out of habit, like to have a positive coefficient with my variable whenever possible. So rather than subtracting 9b from both sides to collect the variable on the right side of the equation, I'm going to subtract 8b from both sides of the equation and collect my b's on the left side of the equation. So 8b minus 9b is just 1b, or b, but I'm still subtracting 12. And on this side, I have just the b's canceled out. I'm left with 0 added to 6. So I'm just going to write the number 6 here. As you get more accustomed to these problems, it would actually be okay to do kind of multiple addition subtraction steps at the same time. But when we're first doing these problems, I do find it students make fewer mistakes if they do each step one at a time. I'm not going to add 12 to each side of the equation because my goal is to get b all by itself. And so I end up with b equals 18. Once again, let's check this number, make sure we get equivalent expressions on either side of the equal sign. So I've got 3 times 18 minus 4 equals 1/4 times 32 times 18 plus 24. So this works out to be 3 times 54 minus 4. And is that the same thing as 1/4 times 576 plus 24? You can just plug this into your calculator and confirm that each side of the equation is equal. If you multiply this out, it does equal 150. Multiply this out, it does equal 150. So yes, our answer checks out. Now, up to this point, every question we've done, we've gotten a solution, checked it, the solution is checked out. That doesn't actually always happen. And when you see a variable appearing more than once in an equation, you're more likely to get special cases where you don't get a solution that you can check out by plugging it into the equation. So let's see what this might look like. Again, we're just solving each equation, so I'm starting by simplifying. Use the distributive property. 3 times 5c is 15c. 3 times 2 is 6. And I have 15c on this side. Now, next step, combine all the c's together on one side of the equation. I'm going to subtract 15c from both sides. 15c minus 15c is 0, so I've just got 0 plus 6. 15c minus 15c is 0. My c actually entirely disappeared from this equation. I am left with an equation that is false because my equation says 6 equals 0, and that is not true. That is never true. When this happens, your equation actually has no solutions. An equation with no solutions is just that. There are 0 solutions. No matter what value you plug in for c, this equation can never work. So that's one type of answer that you can see. Another example, let's look at this problem. N divided by 6 equals negative n divided by 6 plus 1/2. In a problem like this, where you have a lot of fractions, one of the easiest ways to address a problem like this that has a lot of fractions is to multiply by the least common multiple of all of the denominators. So if I choose to multiply each side of this equation times 6, 6 times n divided by 6 just leaves you with n, like the 6 and the 6 cancel out. On this side, we have to distribute the 6, distributive property, multiply everything you see here by 6. So negative n divided by 6 is just negative n. And then 1/2 times the 6 is 3. This is now a much easier problem to deal with because none of my values are fractions anymore. So now here I need to collect all my variables on one side of the equation. I'm adding n to both sides, and I get that 2n equals 3. Now, please notice the difference. A lot of times when students see a problem like this, they think that the n cancels out. I've got an n on the left side and a negative n on the right side, and they think that somehow the n disappears. If n and negative n are on the same side of the equation, n minus n is 0, but this n and negative n are on different sides of the equation. And so you can see when I add n to both sides, I end up with 2n on the left and 0n on the right, just with a 3 left over. Now to get n all by itself, I divide both sides by 2, and I get that n equals 3/2, or if you did that on your calculator, you might get the number 1.5. We've got a solution. Let's go plug it in and check our answer, make sure it works. 1.5 divided by 6 equals negative 1.5 divided by 6 plus 1/2. And now you can plug that in your calculator is perhaps the easiest way to do that. This turns out to be 0.25, and that equals negative 0.25 plus 0.5 if we kind of convert them all to decimals. And then it's easier to see that, yes, this does in fact check out. So remember, it is possible to just get a one solution answer. This problem has one solution. And we've checked to confirm that it is in fact a solution. Last example, in order to solve the equation, I need to simplify first. So negative 2 times 4d is negative 8d. Negative 2 times positive 1 is negative 2 equals negative 8d minus 2. Perhaps you already see the pattern that's appearing here, but let's confirm. Let's see, we're going to add 8d to both sides of the equation so that we can consolidate all of our variables on one side. On the left side, I'm just left with negative 2. My d's also cancel out on the right side, and I'm just left with negative 2. Look at this equation that I have here. This is just a true statement. It's not really an informative, helpful equation. It doesn't say d equals something. It's just negative 2 equals negative 2. This is a true statement. It's a statement that is always true. When something like this happens, we call this, we say that it has infinite solutions. Another way of expressing infinite solutions is just saying all real numbers. Okay, so in this case, there is no one solution. Any value that you plug into this equation, any value that you decide to choose for d, will make this equation true. Let's look at a real life example of how to use equations that have variables on both sides. A boat leaves New Orleans and travels upstream on the Mississippi River for 4 hours. The return trip only takes 2.8 hours because the boat travels 3 miles per hour faster downstream due to the current. So we want to know at what speed did the boat travel upstream, and then how many miles did the boat travel upstream. So remember, one of those equations that you're supposed to know is speed equals the distance divided by time. Okay. If we use this equation, another kind of way to think about this equation is saying distance is speed times time. And we're going to look more at how to rearrange formulas like this in a later section of this chapter. But if we want to compare the distance upstream has to equal the distance downstream because this boat made a round trip. However far it went up the river, it went the same number of miles down the river. But the speed and the time are different upstream. So the speed going upstream times the time going upstream, those values are going to be different to the speed going downstream and the time going downstream. So now we can plug in the values that we know. We know that the speed up, we don't know the speed upstream, but we do know that the time going upstream was 4 hours. We don't know the speed going downstream, but we know that whatever the speed is, it was the same speed as before plus an extra 3 miles per hour. And then the time going downstream was 2.8 hours. So we've just used our distance upstream equals distance downstream, replace distance with speed times time, because we know the relationship between distance, speed, and time. And then we plugged in the values we know, and we've got one variable to represent the speed upstream that we don't know. Let's simplify both sides of the equation. Speed times 4 is just 4s. Here on the right side of the equation, 2.8 times s is 2.8s, and then 2.8 times 3 is 8.4. And now I want to consolidate all my s's on one side of the equation. So I'm going to subtract 2.8s from both sides, and I'm left with 1.2s. That looks like a 5. The 2.8s minus 2.8s leaves us with 0, and we just have 8.4 on the right-hand side. And now I can divide both sides by 1.2, and I'm left with s equals 7 miles per hour. 7 miles per hour is the boat's speed upstream. Now, how many miles did the boat travel upstream? Remember, distance is speed times time. So upstream, if the boat was going 7 miles per hour and it was traveling 7 miles per hour for 4 hours, then the boat traveled 28 miles. So this is how an example of a real life problem where the variable appears on each side of the equation, but we can use the strategies we learned in this lesson to solve the problem. I hope this helped.